The so-called dielectric constant for a material is defined as the ratio of the permittivity epsilon for that material to the permittivity of vacuum epsilon naught. When we first talked about it, I warned you that for a thing referred to as a constant, it's about as non-constant as something could possibly get, and it's time to deal with that in a little bit more detail. Most relevant to us is the fact that epsilon in just about every material is a strong function of frequency. Just as a quick plausibility argument, let me remind you that the permittivity for a material basically measures how readily the atoms in that material will polarize. I've never written that particular equation before, but trust me when I say that it comes in a straightforward fashion from the definitions of P, E, epsilon, chi, and all those good things back in Chapter 6. What this is basically saying is the farther epsilon diverges from epsilon naught, the more polarization per field you're going to get. And it's not too big a stretch to imagine that if I try to polarize an atom real slow, drag that charge off real slow like, it's going to respond differently than if I were to try to yank that electron cloud back and forth real fast. And hence the variation with the frequency of the applied electric field. And since the index of refraction ultimately comes from epsilon, that means that the index of refraction is a strong function of frequency also. And that means that different colors of light will refract differently, leading to awesome things like rainbows. The variation of index with frequency is known as dispersion, and it's not just for rainbows. Dispersion is a really big issue in optical engineering. When you have a multi-wavelength source, the fact that the different wavelengths propagate in different ways through your devices turns out to be one of the dominant issues for a scientist or engineer to overcome. But regardless, this is a thing that matters, and we're going to get an entry-level understanding of dispersion by looking at a classical model, starting from the idea that time-dependent E-fields drive electrons about a nucleus in the form of a simple harmonic oscillator. So what we've got here is the equation of motion describing the position of some electron relative to its nucleus. We've got the old mx double dot on the left. The first term on the right is a linear restoring force. I should point out that it is kind of absurd to model an electron as a ball on a spring, but not as absurd as it might seem. If you prefer, don't think of it as a ball on a spring, just think of it as an electron having a linear restoring force as you pull it away from a nucleus. And pretty much everything, when you're near equilibrium, undergoes linear restoring forces, because pretty much every potential you can imagine, no matter how complicated, if you're near an equilibrium point, you're going to be able to match that locally with a parabola. And a parabolic potential leads to a linear force since it comes from the derivative. Anyway, let's get back to that equation of motion. The second term on the right is some sort of damping force proportional to the velocity of the electron. And the last term is the driving term, the electromagnetic wave that's incident on this material, and that's the term that's frequency dependent. So here we have a damped-driven simple harmonic oscillator equation. In theory, you're proficient in solving such differential equations by now and can quickly obtain the steady-state solution, which looks like I'm putting some extra frills on the k in this equation so that I can distinguish it from the wave vector k that's going to show up very soon. Now, here's the tricky part. What we're actually working towards is finding the index of refraction as a function of frequency. And I claim that that information is hidden somewhere in this position versus time equation. We know that n is c over v, and v is 1 over root epsilon mu. So getting epsilon out of that snarly mess would be good enough for our purposes. Here's how we do that. The definition of the dipole moment, P, is q times d. And P is also equal to alpha E, which is just saying that it's proportional to E in linear materials. And that QD term, we can put that in terms more relevant to what we're doing now by letting the charge be the electron charge E and letting the distance vector be the x vector. So let's rearrange the above a little. Multiply both sides by minus E. and it becomes immediately apparent what that constant alpha is. Next step, keep in mind we're trying to find epsilon, which is a macroscopic parameter. So maybe we should try to convert this little p, the dipole moment of a single polarized atom, into big P, the polarization, which is the dipole moment per volume. Supposing there are new atoms per cubic meter of this material, we can write the following. Let's also go ahead and write the relationships between the macroscopic fields P, D, and E, which, if we factor it, lets us figure out what epsilon is in terms of that parameter alpha. So epsilon is given by epsilon naught plus nu alpha, giving us what we wanted, epsilon with an explicit frequency dependence. So this is kind of interesting. If we use a model that has a damping term, shown by that gamma, we end up with a complex permittivity. If you want to, you can then say that the index of refraction is complex also, and come up with rules for interpreting that, but I think it's easier to treat the index as always being pure real, since it's a ratio of wave speeds, and that means we need to find another way to split out that complexity. Remember that the wave vector k is equal to omega over v, and v is 1 over root epsilon mu, and epsilon is complex, so we could make the wave vector complex. That means that we can write it as the sum of a real part and an imaginary part. So a plane wave propagating through this material will take on a form like, and so the real part of the wave vector will give us a nice normal propagating term, with the imaginary part being responsible for attenuation, just like back in evanescence and also in waves and conductors. So let's just focus on the propagating term for now. That part of the wave vector is what's responsible for the speed of the wave, which is what's relevant to the index of refraction. So when we use n equals ck over omega, we can just put the real part k1 in there. And that part will still have a frequency dependence, so now we've isolated a purely real n with the appropriate behavior. Now if you really want to, it's possible to actually go through and solve for k1 and k2 in terms of the stuff from our previous expression, and do a bunch of algebra and get the following. You can also take the imaginary bits and roll them together into a characteristic absorption length. This is the distance it takes for the light to drop to 1 over e of its original intensity. And as you can see, when gamma is big, this distance is short, and so the light attenuates quickly, and when gamma is small, the light takes a long time to attenuate, which kind of makes sense since gamma was the term that showed up as our damping constant. Alright, so what we've got here is two different parameters graphed versus omega over omega naught. One of the curves is n minus 1, so it's just the index of refraction shifted. And then we have that characteristic length d, or more properly, its inverse. The point 1 on the horizontal axis is when omega is equal to omega naught. And you'll notice that for the most part, that function we got describing n versus omega is fairly well behaved and boring. N goes up a little bit, and generally increases with frequency, and not a whole lot really happens to the absorption length either. But when you get close to that omega equals omega naught point, everything goes kind of crazy. The index of refraction changes rapidly and starts going down instead of up, and the absorption length drops tremendously, meaning that the distance it takes for a certain amount of absorption to happen is much shorter, meaning absorption is happening much faster. What we see here is basically a resonance. When omega equals omega naught, which you can call a resonant frequency, you're going to see a very strong absorption. And as you get farther and farther away from that resonance, everything gets back to normal. In real materials, you can have lots of different resonant points and a very complicated structure, and we'll take a look at such a graph in class.